All right, so we are working just to kind of consolidate our past 2 lessons here. What I would like to do is just do like a culminating question which wraps up day 1 and day 2 really nicely. So I think if you have some questions maybe from the past couple days, this will be a good answer to some of your questions. So we'll just get cell phones off desks, put them away. We need to just focus in here. The trade-off to you doing the test questions today is that unfortunately you don't have time in class to work on the assignment that I'm going to give you, so you will have to do it over the weekend. So I trust that that is a reasonable trade-off. Okay, so for this function f at x, we are going to find out a bunch of information, and we're going to create a super accurate sketch. How does that sound? Woo! Thank you. All right, so we're going to find the solutions or the x-intercepts to this function. We are also going to find the y-intercept, which we can get from the original function. No derivatives needed for those 2 things. We're going to find any local extrema. We're going to identify them. Okay? Local extrema, we need the first derivative for that guy. And then we're going to talk about intervals of concavity, and for that we need points of inflection, so we need the second derivative for that. Okay? So we're going to pull out all the information that we can about this. Firstly, we know a little bit of information about this function f at x just by looking at it here. Okay? I know it's an even degree polynomial. It's degree 4, so it's U-shaped. Okay? And I know that because the leading coefficient of this is positive, it actually is U-shaped facing up. Okay, so we already kind of have a general shape of our graph, like so. Something like this, U-shaped facing up. Degree 4, even degree, U-shaped, leading coefficient positive, facing up. Okay, moving forward. X-intercepts. So in order to find x-intercepts, we need to first set f at x equal to 0. That's where we're solving for where y equals 0. What is x? Okay, and I think we should be able to do this by common factoring. And this is not a difference of squares, but we can still solve it, right? So we can't factor any further, but I know that here x equals 0. So that's an x-intercept at 0, 0. And in order to solve this guy, we can just set him equal to 0 and then isolate for x here. Okay, so I want to know what makes this equation true, right? So I'm bringing the 6 over, and one thing that we need to be mindful about is when we're solving equations like this, when I take the square root, I take the positive and negative square root of this thing, right? So I'm going to get plus minus root 6. So there's actually 2 x-intercepts, or 2 solutions that we get from that guy. Okay? So we've got our x-intercepts of our function. They come from the original function. Okay? Setting the original function equal to 0 and solving. So we've got an x-intercept at 0, 0. And actually, we know that it is order 2 because the exponent on it is 2. So drawing from some previous knowledge in advanced functions. And we also have root 6, 0, order 1, and a negative root 6, 0, also order 1. Okay, our orders should add up to the degree, okay? So the degree of this guy's 4, and my orders are 2, 1, and 1. They add to 4. That should make sense. How do I find the y-intercept of this function? What's that? Which x am I plugging into the equation, though? What is x on the y-axis? 0. So we're going to sub in 0 for x, and we will solve for the y-intercept. Okay, so we're evaluating f at 0. Well, we kind of already have it, right? Because we have an x-intercept already at 0, 0. But if you had to solve for it, we would sub in 0 for x. So we actually know that the y-intercept kind of already from looking at the x-intercepts is 0, 0. But if you need to solve, it's there for you. Okay, we're going to box up that information. We will use it later. All right, so these guys, X-intercept and Y-intercept, we get from the graph of f at x, or the function f at x. Local extrema, I'm going to get from the function f prime at x. Zena, question? Well, I subbed in 0 for x, and I got out 0 from the function, so that's the point 0, 0. And we're finding the y-intercept, so anywhere on the y-axis, x equals 0. That's why we sub in 0. Okay, so moving forward, for the first derivative, we're going to find what we can about the local extrema, or the critical numbers of this function. So let's take the derivative. And we find critical numbers where the first derivative is equal to 0. So I'm going to set that first derivative equal to 0. And I think we can common factor from here a 4x. And we're left with x squared minus 3. So actually, this is kind of a similar solving process for what we did last time. We've got a critical number not at the point 0, 0, but we have a critical number at, well, actually, the y coordinate for that is 0. But we have a critical number where x equals 0. Sorry, I'm just talking to myself. And then we're going to solve this guy. Again, making sure that when I take the square root, I take the positive and negative square root. Okay, so those are my critical numbers. They're not my critical points. They are the critical x values, 0, root 3, and negative root 3. Mark?
Do points POIs, are they points or are they just the x values?
POIs, points of inflection, we can find the x values, but when we say point of inflection, we're talking about xy coordinate. Okay, just like if I say critical point, I want the xy value of that point. Okay, and it's actually useful if we're creating kind of like a full sketch and I'm looking for local extrema. I actually want to know the xy coordinates of those things. So I can find the y coordinates for these points. So if I want to write them as points, I'm going to sub them all into the regular function f at x. Well, I already know that f at 0 is 0. So we know that the critical point there is going to be 0, 0. And then I would also want to know f at root 3 and f at negative root 3 to get the actual point of that. Okay, so we're subbing that into the original equation. And actually, our roots should kind of not really matter once we sub them in, because we're putting them to the exponent 4 and exponent 2. So that actually works out nicely for us, where those kind of cancel out. So I've got 18 here and 9 here, right? So negative 9, is that right? Maybe I'll just move this down here. Okay, so here's another critical point. It's at root 3, negative 9. And I think we actually get the same thing when we sub in negative root 3, right? Because we're putting them to the positive or to even exponents. So the negatives just become positive anyways. So I think we get negative 9 again for that negative root 3. Okay, so we've got another critical point at negative root 3, negative 9. Okay, so we're subbing these in not to the derivative equation, but to the original equation to find the y coordinates. Okay, can somebody tell me, like, what are these points that I just found here, these critical points, where the first derivative is equal to 0? What does that tell me we have at some of these possible areas? We have turning points, and some of them will be local maxes, and some of them will be local mins, right? I know whether they are local maxes or mins by looking at my chart, okay? Or I can create a sketch of this function if I want, but why don't we go ahead, we'll make a little chart here, first derivative chart. And I want to put each 3 of these on here, so it will be lowest to highest. So I want 1, 2, 3, and then I'll do a final line for infinity. And then we will draw what that tells us about f at x. So you don't need to put the whole point here. You can just put the x value. Sorry, negative root 3. And positive root 3 and infinity. Okay, so it might be helpful for us to just be aware that the square root of 3 as a decimal is about 1.7. Just when we're picking our test values, we need to be mindful of that. So we've got kind of like negative 1.7 and positive 1.7 here. So we're going to choose some test values for this guy. So I need something between negative infinity and negative root 3. Maybe we choose like negative 4. And then maybe we can do positive 4 over on the other side here. And now I need something between negative 1.7 and 0. So maybe I choose like negative 0.5. And then same idea, but on the positive side, maybe I'll choose positive 0.5. Or actually, you know what? Why don't we choose negative 1 and positive 1? That will be easier. I think that's a good idea. Okay, so we're summing these guys into the first derivative, and we are recording positive and negative. Okay, so you can sub into your factored form or sub into your original, whatever you want to do. That's totally fine. Okay, so I'm going to give you guys a second, sub those guys in, and see whether you get negatives or positives. Okay, so I got negative, positive, negative, positive. Agreed? Is that what you guys got? Mark? No? Did you get something else? Well, you guys tell me. I did it all in my head, so. You got that? Okay. Okay. Perfect. So I know where the first derivative is negative. My function f at x is decreasing, which is why I'm showing the arrow going down. Then we've got that critical point, and then it's increasing. And then we've got that critical point again, then decreasing, then increasing. So I think we can see now if these points are local maxes and local mins. This guy is going to be a local min. This guy is going to be local max. And this guy is going to be local min. Nope. We haven't done anything with second derivative yet. These are critical numbers, or local extrema. They're like turning points, the tops of turning mountains and valleys. Second derivative will give us those changes between concavity. Olivia. We already did that right here to get the y coordinates. Okay? Now, because this is U-shaped, we actually will not have an absolute max because it's U-shaped and going up forever. So there's no absolute max. There's a local max, but not an absolute max. There should be absolute mins. And because I have two local mins that have the same y value, both of these are actually absolute mins. Okay, so they're local mins, and then they're also the absolute lowest point of our graph. Okay? No absolute max though, because it goes up forever. Okay? So these are also absolute mins. Any questions so far? Okay? Now, the last thing that we're going to do is observe what happens with the second derivative. That will tell us about areas of concavity and exactly where those change. So we're going to do that. So concavity and points of inflection, we're looking at f prime prime. And we're going to create another chart that helps us with that. Okay, so f prime prime at x. 12x squared minus 12. And in order to find points of inflection, we're interested in where our second derivative is equal to 0. So I'm, again, common factoring here. And, oh, interesting, x squared minus 1. This looks familiar. Looks like it maybe occurred somewhere on your test that you just did, which is a difference of squares. Cool.
Did it? What did it actually? Yo, a difference of square. Oh my god. There was no difference of squares. What?
I am so glad because it's more factor.
No, there
I am,
wasn't.
I am so glad.
Which one?
It's the very last question, right?
Actually, the last two questions.
The last two. Oh wait, this is actually.
Okay, moving forward. Focus in here. I should not have said that. I didn't look.
No, it wasn't. No, it was x2 plus x minus 1. Yeah, it was. That wasn't in the denominator.
Yeah,
I swear that wasn't
for
in
number 3. No, number 4.
Okay, shh. I'm going to find the points of inflection by subbing in to the original function to get their y coordinates. So I want to evaluate f at -1 and f at 1. So my original function will do, I think it'll actually give us the same coordinate here. And then minus 6x squared. So we should get -5. Okay, so my points of inflection are at -1, -5, and also +1, -5. So this is starting to look to me like this is kind of like, it has some symmetry going on, right? There's some points that I'm getting some of the same y coordinates for, so even degree. It also has all even exponents, so we should expect that there's an element of symmetry happening here. That won't always happen, but here it's happening. These aren't x-intercepts, these are just the x coordinates of the points of inflection, but we're going to sub them in to get the y's. Okay? Okay, so we're going to do one last chart with our concavity. So I am interested in where those changes are happening exactly, over which intervals. So I've got 2 points of inflection. Okay, so I chose some test values between those intervals, and I'm plugging them in not to my original function, but to the second derivative to see whether we get positives or negatives here. So I think we get positive, and then negative, and then positive. Okay, positive tells me not increasing or decreasing, it tells me concave up. So it tells me this for that section. And then I've got a point of inflection here, so that's where it changes. And then I've got a section that's concave down. And then I've got another point of inflection, and I have a concave up area. Okay, so just remembering that this is a point of inflection here. Olivia. We did to get their y coordinates, but in this chart, I'm plugging all of these into the second derivative and recording positive, negative. Okay? That's why we have second derivative here. That's what we're subbing into. Okay, we have a ton of information here. So let's plot all of our information. So first, let's just go through. We're going to plot all the points that we found, that we boxed up. So X-intercept, Y-intercepts, or X-intercepts, Y-intercept, critical numbers, and points of inflection, and then we'll fill in the gaps with all of our information from our charts. Okay? So X-intercepts are happening at, like, we're going to have to kind of approximate this, but root 6 is like 2.449, so 2.4-ish. So let's just start with X-intercepts. We'll do 0, and then how far do I need to go on the x-axis here? Not too far. So maybe we can spread out our scale here a little bit. I just want to see what I did on the previous lesson here. Oh, here we go. Spread out our scale. Yeah, that looks good. So we'll do 1, 2, 3, 4. And then I'm just going to do these ones regularly. So this will be 2, 4, 6, 8, and so on. Okay, so I'm going by 0.5s on the x-axis, and I'm going by 1s on the y-axis. Okay, so let's plot these guys. I've got one at 0, 0. That's also the y-intercept. And then we said root 6 was like 2.4-ish. So I have one at negative 2.4, and I have one at positive 2.4. That was not right. Negative 2.4 and positive 2.4. Okay, so those are x-intercepts. Okay, points of inflection, I'll do those in blue, or sorry, critical numbers, I'll do those in blue. We have them at 0, 0, which we already have plotted, and then root 3, negative 9, and positive root 3, negative root 3, negative 9, and positive root 3, negative 9. So that's about 1.7 and negative 1.7. So we're going to put these both down. Negative 9 is, we can just draw it on here, negative 9 is right here. No, I'm going by 1s on here. I just labeled it, not every single tick. So negative 1.7 and positive 1.7. Those are our absolute mins. And this is our local max at 0, 0. Okay? Yep, we're drawing f of x. And then points of inflection, our last ones are at negative 1, negative 5, and positive 1, negative 5. So here and here. Okay, this should give us a pretty wide area, a pretty wide amount of information here. We should be able to get like a really great sketch here. Mark? The blue dots are the points of inflection. So I'm just going with the colors that I used up here. Blue dots are points of inflection, and I guess I should have done these guys in purple. Purple are points of inflection. Blue are local mins and maxes, turning points. Okay, so I know from in this first section right here that my function is decreasing. Okay, so looking at my chart, I can see that it's decreasing. It's also concave down up to, actually I'm going to do these in red so you can see them a little bit better. Up to this red part right here, I change from increasing, but it's still concave up, okay? So I'm increasing now, but it's concave up. And then when I change into that next section from this negative 1 to positive 1, I am concave down. Okay, so we're just kind of filling in the gaps here. So here I should be increasing and concave down, and then decreasing and concave down. Okay, and then we're changing to concave up and connecting the rest of the dots there. That's a really good sketch, right?
All this.
Pretty solid.
All this for that.
Okay, maybe I should actually just fix this. It doesn't look amazing. There we go. Cool. Okay, so if you want to label these guys, you can. These were our local extrema or our critical numbers. So you don't have to label, but some people were asking me what they were, so this is also local extrema. Okay, and then my red ones here were points of inflection. Yep. Okay, and then these guys were X-intercepts. And this was both X-intercept and Y-intercept. Cool. Okay, one last thing. I just want to review to you the second derivative test and how we use it and why. Any questions on this before we move forward? Olivia. Okay. Okay, so second derivative test with critical numbers. So this is what we were talking about yesterday. This is one of the ways that we can use the second derivative. So the first way that we've used the second derivative in this example is finding intervals of a concavity. But we can also use the second derivative test with our critical numbers, and I showed you a chart of that yesterday. But you can also do a really quick test by subbing into the function. So this helps us decide whether they give, when we have a local max or a local min. So it helps us, maybe we'll just say identify local extrema as local max versus local min. Okay. So let's suppose we just kind of take a look at our function above, because we already have some of those some of those points. We had the function that looked like this. And we found our critical numbers on this function when we found the first derivative and set it equal to 0. Gave us critical numbers of, what was it, root 3, negative root 3, and 0. Was it root 6? No, it's these guys here. Those were the zeros, right? Okay, it gave us critical numbers of these 3 guys. Okay, now when I find the second derivative, which we did above already, we can test the second derivative just to really quickly decide if we have local mins or local maxes. So we will test these in f prime prime of x, which we know was 12x squared minus 12. And this is the really quick test that we can do. So we didn't do this above, but this is kind of like an alternative to creating the charts to find whether it's local max or local min. So what I would do is I would just sub in 0, root 3, and negative root 3 separately. And I'm just kind of interested in not necessarily the number, but I'm interested in whether it's negative, positive, or 0. So if I test this in here, we can see that we get negative 12. And because that's less than 0, it will actually tell us that we have a concave down area where that particular x is, right? Negative means concave down. So what this tells me is my point a local max or a local min if that area is concave down? It's a local max. So therefore we know we have local max when x equals 0. Okay, and then I'll do a quick little test in here with root 3. And we'll see what that gives us. So again, I'm mostly concerned whether positive or negative, but if you want to calculate it, that's fine. So I think we get 24. And because that's greater than 0, I have a concave up area, telling me that at root 3 we have a local min or max? Min, yeah. So therefore, local min when x equals root 3. And then lastly, we can sub in negative root 3. I think we'll get the same thing because we're squaring it. But we'll just kind of show here. I get another 24, which is also greater than 0. That tells me that that area of my graph is concave up. And I have another local min at that value. Okay, this is what's called the second derivative test. So we plug in the critical numbers into the second derivative, and it helps us find whether that area is concave down or concave up. Okay? One other thing that you should know is that, this is kind of important, if I sub in to f prime prime, and I put in my critical number, and I get 0, that's an interesting one, right? Because that area is neither concave up nor concave down. That actually tells me that I'm looking at a point that is a point of inflection. This test fails, and then we're going to refer to the initial interval chart for the first derivative. So our test will fail, and we will refer to the first derivative chart. And basically, sometimes this can be because you have like a point, you might have like a point where we don't change, like maybe the derivative is equal to 0, but we're not changing like from increasing to decreasing, so that could happen. Or maybe we have like a specific point where the derivative is undefined, something like that. So that's kind of scenarios where we want to refer back to the derivative chart, and maybe we'll see increasing. We'll say, oh, that's neither local max nor local min. Okay, cool. So you guys actually have a little bit of time to work on your assignment.